Thank you. Right, this matching number is coming from graph theory, and this work is a collaboration with Kazunori Matsuda, who's doing combinatorics and commutative algebra. That is, he's a mathematician, and this is also a collaboration with his students, and now our student Yosuke Tsuji. So this started as where I got some math input from Kazunori about graph theory and commutative algebra and its relation between them. Kazunori is very good at devising examples and counterexamples, and I suggested him. Uh, uh, shall I continue? Oh,
I'll ask him to turn it
so,
on.
looking at his proof, it involved a lot of induction, a lot of case analysis. So I asked him whether he is interested in formal proofs. So and he said yes. So it started the collaboration. Okay. This presentation is mostly not about the proofs, but about the struggle in the definitions. Let's go with the motivation. Is before the motivation, the graphs we deal with is like this. It allows several edges between vertices, but it doesn't matter so much in our formalization. It can be anyway eliminated by adding some condition. Important point is we are using types of vertices and edges. They are actually finite types of vertices and finite type of edges. And mapping function that gets the boundary from an edge. So the resulting set should be of cardinality too. That is an informal definition. Okay, usual graph, not so much unordinary. And can I remove that bar? Okay. There is written a motivation. What is written? Motivation is the relation to ring theory, I think. Yes. Sorry. Okay. Thank you. The relation is very straightforward at this level of definition. Given a graph, there are vertices and edges. And we take vertices to be variables, abstract variables like x and y. And assume a commutative ring, then we can construct a polynomial ring out of a graph G, assuming the number of vertices is finite. And also, we can construct some ideal from the edges to be taken as an information to construct ideal. There are edges with xy vertices, then we put in a monomial xy into the set of generating ideal. By this way, we can have a quotient ring dividing S by I. That is a usual operation that ring theorists do. Then there are, honestly, I do not understand ring theory part yet after getting input by Kazunori, but there are some invariants on the ring side, like dimension, regularity. They are usually constructed by chaining, quotienting, but starting from this information. They are sometimes different numbers, sometimes they are same numbers, but their bounding is usually very difficult to obtain on an arbitrarily commutative ring. But for this case, if it is generated from a graph, it is bounded by invariance on the graph side. That is something interesting. So we wanted to formalize this thing. So we have to do two things, ring theory and graph theory. And so far, we finished doing graph theory side. Okay. The graph invariance we want to talk about is matching sets. Matching set is like a marriage problem. We have to we take several edges out of a graph. Then these edges should not have an overlapping vertex. That is good matching. And induced matching is even more separate matching, that no two edges can be in between two given edges in the induced matching set. Okay, we have a nice picture, a nice drawing in the next slide, so please wait for until that. But matching number is a maximum size. Induced matching number is a maximum size of an induced matching. One somewhat twisted case is a minimum matching number. It's a minimum size of maximal matching sets. There can be many maximal matching sets. Maximality is just a set inclusion, so it can be larger or smaller, but we consider the minimum size of them. Okay, so one picture is like this. On the left picture, as I showed, the E1 and E5 on the left and right hand side are consists of a matching, and E2, E4 the same. But there is no induced matching that contains more than 2 edges. On the other hand, on the right graph, there is an induced matching that contains 2 edges, F1 and F4, since it can be separated by F2 and F3, 2 edges between. Okay, so induced matching is a bit separate. And their numbers can be quite different between graphs and graphs. Okay. And we also consider another invariance, but I haven't drawn a good picture. But it is about the vertices. There is something called the independent set about the graph. That is a set of vertices that does not have edges between those vertices. Okay, that is also a part of the formalization. So what we achieved so far is basically these inequalities. You see, some of them are quite straightforward, like enemy match less than n match is straightforward, since it was about the minimum number of maximum matchings and maximum number of maximal matchings. But between induced matching and 2 times enemy match doesn't look very straightforward, or do they? To me, it was not very straightforward. And also some things involving independent numbers and in depth is also not quite immediate. So we have to do some combinatorics. And to do some combinatorics, what we had to do is manipulation of sets of vertices and sets of edges. So what we now have to do is to formalize those sets in a good way. How much time have passed? Okay. The first attempt, okay, thank you. We will have to first formalize the graph, and we tried 2 ways. First attempt was a very classic way of using Roq. Define a module, put in a single type module, type T in a module that represents the module, and just written down the definition. You see, it is exactly the translation of that informal definition, and export the handy notation and use it. No canonical structure, no hierarchy builder so far. And this worked well, but soon later we wanted to experiment some extensions to these graphs, like adding completeness axioms to it, or maybe other, like the graph does not have whiskers or like that. Those axioms are to be added in a future development. Actually, we started only complete graphs, but and for doing that, this naive module representation of graphs was not very satisfactory. We wanted to use the hierarchy builders as introduced by Renault. It is very good for introducing axioms one by one. So try to do it also in terms of HV mixing and structure. Looks almost the same, but now the set of axioms and the declaration of types is separate. And okay, it looks almost the same. Somehow I had to change the names from V to vertex, since the name vertex and edges are exported. I didn't want to use very short names, but that's the only change so far. Okay, and the transition of the remaining code to this new HP definition was amazingly easy. Almost nothing had to be changed. See. 2 things had to be changed. One, the constructor MK, the type constructor MK in the module had to be changed by HP instance definition. That is a declaration of instance, and that's basically the only long thing. And one other unexpected change was this. Backtick D is, you see, coming from the field in the mixin. So it is hidden somewhere inside the HP definition. In the concrete case, we should be able to unfold this into the original concrete definition. But it was not immediate. But inserting this trivial equality, relied stating some proof and D equal D prime, and this is immediately solved by // that is just applying reflexivity. So it must be just a reflexivity. But this needed because we could not just unfold backtick T. Unfolding backtick T reveals the internals of HP, so it will be very difficult to proceed with. But this is the only addition in the proof side. You can see that even with the HP structures, it is easy to construct a concrete example from like 3-point set and 2-point sets, and we work with a very actual example of graphs. It is not just about theory, but also it can also handle with examples. Okay. But one thing I couldn't understand, but maybe a glitch, is that the key type here, the unit, you see the HP instance definition line, there is a first argument unit and second argument axiom. The type unit is a first argument that is taken to be the key to this structure. And it means that we are endowing this graph structure to the type unit, but the unit can be arbitrary. It is not completely unrelated to the mixing. So I somehow maybe abused HP. Maybe I should have taken V, the type of vertex, or the type E or edges to be the key, but I didn't see which is better to be chosen, and choosing them did introduce some complication. Choosing one of them as a key and as a parameter, then it doesn't provide us a projection to that type. Maybe not a problem. Maybe we just do not need a projection, but somehow it worked in a weird way. Okay. Oh, maybe not okay. Okay. Then we proceed to the sets of edges or graph edges of vertices. How many times? Sorry. Let me say. Okay. Thank you. Okay, then graphs are settled. The definition of graph seems to okay. Then we want to proceed into sets. And there are many libraries for sets in mathcomp families. At least 3 I know. Set in mathcomp proper, it is about finite sets in finite type. Then fset is meant to be an extension to these finite sets, and it relaxes the condition on type to choice type, that is locally satisfying the axiom choice. These are types coming with canonical choice function. Both of these finite sets are implemented as list representation. First, in the mathcomp case, by enumerating T, because T is a finite type. Taken from the type can be canonically linearly ordered. So they arbitrary sized sets in arbitrary type. So it cannot have any list representation. It can only be a wrapper for crop predicates. Okay. So we need a cardinality of each matching set because we want to think about the maximum size of matching sets and so on. Each matching set must be a finite set, so we have to choose either first or second implementation. And finmap S sets work better with other two. On the other hand, the first and the third mathcomp-classical sets conflict in notations in a very bad way. So I didn't want to mix them, and so we chose the finite finmap S set. And there can be still there can be a design choices between how to express the set of all matching sets that is needed to take a maximum. I could go with either finmap or classical at this point. I first tried to use finmap to represent the set of all matching sets. That is the definition matching. You see the type is f set of edges. And it is straightforward. Only nasty thing is that the predicate is matching has to be presented as a Boolean predicate, the bracketed one. That is not straightforward to use. It is not just a function type. It has to be reflected back to prop to be actually usable. Okay. Doing classically, this problem disappears. We can use just the usual proposition definition in terms of proposition operators. And the definition of set looks almost the same. Okay. And matching numbers can be amazingly, it was a bit amazing, but could be defined with the same expression, matching equals taking maximum over matching. Here, matching is interpreted as a type. So we range S over the type matching, set matching regarded as a type, and take all the cardinality and take the maximum. Yes, this must, so the condition, the necessity for the max is that the matching must be a finite type, and finmap F set is has a coercion. Each finite set has a coercion onto a finite type. And in the classical case, there is also a coercion. Each classical set A is coerced into a sigma type. But here is a one technical. I very much like this technical development that you see X in A, not like A applied to X. Writing X in A, there is another coercion from prop to bool. I said prop to bool. It exists because we are using classical library. By this way, this sigma type is a sigma type, but with a Boolean predicate. And for sigma type with a Boolean predicate, there is a subtyping, canonical subtyping in mathcomp library. So the finiteness of A is inherited into this set type. This is how it works. This is how it made this n-match definition work for both cases. Okay. And other invariants. Induced matching and maximal matching are defined with similar predicates. But you see, the maximal matching is contains explicit S in matching part in the definition of the predicate that we really want to avoid, that we really want to eliminate by using, say, HB. This is clearly an inheritance condition. So before talking about HB, let me say a bit about the comparison. The finmap was good in the sense that we had to only deal with finmap F sets, no need to use classical sets. So only using one library makes the proof look a bit more consistent. And Boolean rewriting works in not many, but some cases, and it is well supported by mathcomp. But bad thing about finmap is, as I said, we have to use the reflection lemmas a lot of many times to work to turn it into a propositional predicate. And classical case, the reflection is almost replaced by just rewrite in E to eliminate the in part. And so the proofs looks I don't have a metric, but looks cleaner in my very subjective evaluation. But there are at the same time bad things that in the classical types, we still have to insert manually the transition between applicative uses of the set to collective uses of sets. I mean AU to UEN, but both ways. And sorry, the bottom side, the bottom edge of the slide is not shown, but wonderful. Well, you know, not in somehow could not be solved by in. That was so nasty, and it is maybe consider the bug and can be improved by writing some code for classical library. But currently, S not in matching is not solved, so we have to modify the proof a bit. Not in a very long way, but the modification itself is not very comfortable. So these are the comparisons. No big difference. No big difference, actually. We could go with finmap, fifth set, or classical sets for the set of matching sets. Sorry for saying something very uninteresting. But as I said, we could go instead. No. There is, as I said, treating these things as sets also imposes us to write these subtyping or subset relations as lemmas, and we have to explicitly use these subset lemmas. That is very uncomfortable because these things are clearly automatable. So I tried to use HP to define the type of all matching sets instead of set of all matching sets, and mixing definition okay, the structure definition okay, the maximum not. Because the type of matching defined in this way is not known to be finite by Coq. I have to endow matching a finite type structure somehow separately. And I can actually do, because this matching defined in this way and matching defined as set has a bijection between them. I can prove that they are bijective. But the use of those bijection is not very notationally clean. So to get to this level of abstraction, I need to do a bit more work, but it is getting to that point. I think it will be pushed to the repository maybe in a few weeks. Okay. Okay. Other invariants, as I said, I implemented also the independent sets and independent numbers. They are rather straightforward. Maybe the proof was not very straightforward. Okay, thank you. And these invariants, inequalities between invariants, they are also proved. Here somehow I have a metric on the length of the proofs. Pen paper 4 and 4 lines, Coq proof. I should have changed this Rock proofs 6 plus 7 lines. After preparing a lot of lemmas on finmap library, I also have our own mathcomp extra.v, as many users of mathcomp users have in their repository. After preparing several things, this factor is not very large. Concluding remarks. Why not Coq graph? I know that I didn't know that when I started this work that there was a Doxcal's Coq graph library. Two things prevented me using that. There was the graph in this library, in their library, was defined in terms of relations. So to my level of knowledge, at that time, it was not clear to how to relate them to sets. And also, we only wanted to undirected graphs, and the Coq graph seemed to be starting from directed graphs and then proceeding to the undirected graphs. So it did not seem straightforward. So I started our work. But now that was a previous situation. Now I should think relating our works to those. It is included in to-dos. And also we have to use hierarchy builder better. Connection start to connect it to ring theory. All I know, mathcomp works for graphs, and we can do even experiments. That's good. Done.